But this is a chart that came from MIT Technology Review, and it talks about the carbon footprint of different things. And the first one is a round trip flight from New York to San Francisco, about 2,000. Then human life is 11,000, American life 36,000. A US car in the full lifetime, so you buy a car until it went into a, until you trash it, it's 126,000. And if you train a transformer model with neural architecture search, pretty much something that most of the industries are doing on a regular basis, that takes 5x more than this. So imagine taking 5 cars, running them for their whole lifetime, and throwing them away. That's the amount of carbon footprint of an NLP training with model search. And that is happening on a regular basis. And what we are not doing is we are not rethinking how we train neural network, right? We know that brain is very efficient, right? But we are still stuck. If you look at the best system out there, even though the systems are evolving, they are still using the same backpropagation algorithm, which was developed in the 80s when computation was not an issue. Now, if you think about it, so a ReLU activation will compute the activations of all these neurons and will throw 50% of them. So you're already throwing away 50% of the computations, because anything that is less than 0 doesn't survive. So you do the calculation and you throw it away. So it's like already 50% wasteful. In fact, there are a lot of research that was going on prior in NIPS 13, 2015, where people said that, well, you don't even have to throw 50%, you can actually throw away 90, 95%. And the way to do this is you take the input and just only take, let's say, selectively few neurons, which has high activation, and throw the rest. In fact, you can sample them in proportion to their activation, and you'll still be fine. Now, their claim was that this actually improves generalization, because most of the parameters are updated only by a minuscule quantity, and maybe that's noise. In fact, if you want to think about it, well, your networks are large, you have millions of parameters, you've been training this network for weeks, and today it made a mistake on an image of a cat. Do you want to go and train all the billions of parameters or millions of neurons based on one mistake? And if you look at the updates, most of them is going to be very small. In fact, they may not matter. Do you want to do that? And in fact, the argument was, no, you should not, because you should just pick like spike neurons or the neurons which are high in activation and only train them. And so we want to see how an implementation of the algorithm that I showed fare with the 2 best industry scale implementation, even on some of the hardwares. And here is, like a snapshot. So on this axis, we are looking at the time per epoch. The blue bars is actually 814 seconds, 300 seconds, 644. These are on CPU using this implementation of the algorithm that we talked about. The orange line is actually TensorFlows, as in like Google's implementation or the software's implementation on the same CPUs. And in reference, we have also put the best top of the line GPU, Nvidia 800, and how much time it takes to train with TensorFlow. Now, this is again like time per epoch, but you may be like, okay, how many epochs do you need to train? That's also not clear. So on this here, we show the accuracy climb of the recommendation model with the wall clock time. And again, note, these 2 wall clock times are on the CPU. This one is on a GPU. So obviously, GPU is much faster than CPU if you use TensorFlow. But if you use a smarter algorithm, things can completely change. Now, this was on a 200 million parameter model. Things starts to become even more interesting when you go to a billion parameter model. A billion parameter model will not fit on your 800 GPUs. So if you have reasonable enough batch size, you need 4 800 GPUs, and then you have to deal with the distributed communication and all. You can still train it. It takes about 1600 seconds per epoch. Whereas if you take an Intel, so this is actually a refurbished V3 Intel processor, which costs you less than $1,000. And if you use the usual TensorFlow, obviously it's very slow. But with our implementation, we are even faster than here. So this is actually pretty exciting.